Energy of a simple harmonic oscillator. Okay, energy of a simple harmonic oscillator. Energy of a simple harmonic oscillator. Okay, the total energy of a simple harmonic oscillator at any time t is the sum of the kinetic energy and potential energy at that instant of time. Okay, the total energy of a simple harmonic oscillator, the total energy of a simple harmonic oscillator the total energy of a simple harmonic oscillator at any time t is at any time t is the sum of its kinetic energy and potential energy at that instant of time instant of time E total equal to kinetic energy plus potential energy. Okay, kinetic energy. The general equation of simple harmonic oscillator is given by kinetic energy. The general equation of a simple harmonic oscillator, oscillator is given by y equal to a sine omega t plus phi. Okay, where y is the displacement and of the oscillator at any instant time t, a is the amplitude, this is displacement, this is amplitude, is the, and omega is the angular velocity, and phi the initial phase are exposed. Initial phase are epoch. Okay, the velocity at any instant. The velocity at any instant v equal to dy upon dt, that is integration differential of y equal to a omega cos omega t plus phi, and kinetic energy of the oscillator. Then kinetic energy of the oscillator, kinetic energy of the oscillator is 1 upon 2 m v square, that is 1 upon 2 m dy upon dt square, that is 1 upon 2 m y dash square. That is kinetic energy equal to 1 upon 2 m a square omega square cos square omega t plus phi. Okay, and potential energy the potential energy is equal to the amount of work done in overcoming the restoring force from the mean position through a displacement y. The potential energy the potential energy, the potential energy is equal to is equal to the amount of work done in overcoming the restoring force from the mean position through a displacement y. Okay. Now acceleration equal to d square y upon dt square, that is minus a omega square sine omega t plus phi equal to minus omega square y. The negative sign indicates the acceleration is directed towards the mean position. The negative sign indicates that the acceleration is directed towards the mean position. Restoring force, but restoring force equal to m omega square y, that is Hy. Okay, where S is the force constant of proportionally or stiffness, where S is the stiffness or force constant of proportionality. Okay, hence total work done by the force through a displacement y, m omega square y, then Sy stiffness. Okay, hence total work done by the force through a displacement y, total work Wt equal to 0 to y Sy dy, that is 1 upon 2 Sy square, that is 1 upon 2 m omega square y square, 1 omega square y square, or Pe, potential energy, equal to 1 upon 2 Sy square equal to 1 upon 2 m omega square y square, that is 1 upon 2 m omega square. The value of y is a square sine square omega t plus phi. Okay, then total energy is kinetic energy plus potential energy, that is 1 upon 2 m differential of y square plus 1 upon 2 Sy square, that is 1 upon 2 m a square omega square cos square omega t plus phi plus 1 upon 2 m a square omega square sine square omega t plus phi. Okay, that is if we take a common, then total energy Et equal to 1 upon 2 m a square omega square common, and left cos square omega t plus phi plus sin square omega t plus phi, but sin square theta plus cos square theta equal to 1. So the value of cos square omega t plus phi plus sin square omega t plus phi equal to 1, and left value is 1 upon 2 ma square omega square. Okay, but omega square equal to s by m. Omega square equal to s by m. S by m. Then hence total energy Et equal to 1 upon 2 sa square. 1 upon 2 sa square, because m omega square equal to s, then also omega, okay, s equal to total energy Et equal to 1 upon 2 sa square. 1 minute. sa square, total energy sa square, that is sa square, 1 upon 2 sa square. So hence E equal to 1 upon 2 sa square, because m omega square equal to s. Okay, then also omega equal to 2 pi n. So Et equal to 1 upon 2 ma square 4 pi square n square equal to 2 ma square pi square n square. Thus the energy of the harmonic oscillator is constant and proportional to the square of the amplitude. Okay, thus total energy of the harmonic oscillator, thus total energy of the harmonic oscillator is a constant and proportional to the square of the amplitude. Okay, maximum kinetic energy. The maximum value of kinetic energy for cos omega t plus phi equal to 1 is given by kinetic energy Ke max. Ke max equal to 1 upon 2 ma square omega square, and maximum potential energy. The maximum value of potential energy for sin omega t plus phi equal to 1 is given by Pe max. Pe max equal to 1 upon 2 ma square omega square. Then kinetic energy max. Ke max is equal to Pe max. P max is equal to total energy. E equal to 1 upon 2 ma square omega square. Okay, kinetic and P half amplitude point. Kinetic energy and potential energy at half amplitude point. Total energy total energy Et equal to 1 upon 2 ma square omega square, then potential energy equal to 1 upon 2 m omega square y square, okay, at y equal to a upon 2, the midpoint of amplitude, the midpoint point of amplitude, the midpoint of amplitude, and the potential energy equal to 1 upon 2 m omega square a square by 4, that is 1 upon 8 m omega square a square, that is 1 upon 4 multiply 1 upon 2 m a square omega square, then kinetic energy, kinetic energy equal to total energy minus potential energy, that is 1 upon 2 m a square omega square minus 1 by 8 m a square omega square, that is 3 upon 8 m a square omega square, and that is 3 upon 4 cross 1 upon 2 m a square omega square, then 1 upon 4 of the total energy, 1 upon 4 of the total energy is potential, and 3 upon 4 is kinetic. PE and KE are equal at potential energy and kinetic energy. Potential energy and kinetic energy are equal to at y equal to plus minus a upon under root 2. Reference examples you can show in next. Then a graphical representation of the energy. Okay? Graphical representation of the energy. 1 minute. Graphical representation of the energy. What is the graphical representation of energy? Okay? Graphical representation of energy. Graphical representation of energy. Okay? The variation of total energy, kinetic energy, and potential energy of a harmonic oscillator with displacement y is shown. You can show this variation. What is the variation and how to work? Then this is a midpoint or null point, and this is so the 0, and this is a plus a, and this is minus a. Amplitude in positive sign and amplitude in negative sign, and displacement y. Okay? Then kinetic energy is starting from minus a and go to max value, and after sometimes decreases again and go to a positive max value, and total and potential energy is if the kinetic energy is 0, then potential energy is maximum, and this is opposite work in this direction, and this is okay. Kinetic energy. First point, kinetic energy. The kinetic energy is given by 1 upon 2 m differential of y square, where y is the velocity of the oscillator, the VE, the velocity, and hence the kinetic energy is 0. the velocity and hence the kinetic energy 0 at the extreme position plus minus y equal to a. Plus minus y equal to a plus minus a plus a minus a plus a. The velocity and the kinetic energy is 0. Kinetic energy is 0. Kinetic energy is 0 at the extreme position y equal to plus minus a and maximum in the mean position. Maximum in the mean position. Maximum in the mean position y equal to 0. Y equal to 0. Then the velocity and hence the kinetic energy decreases. Kinetic energy decreases. Kinetic energy decreases. Okay. Kinetic energy decreases. Okay. The velocity and the kinetic energy is 0 at the extreme position. The kinetic energy is 0 at the extreme position and maximum at the mean position. Maximum at the mean positions. Okay. And y equal to 0. The velocity and hence the kinetic energy decreases. Oscillator moves away from the mean position. Oscillator moves away from the mean position and finally becomes 0 at extreme position as shown by the curve marked by kinetic energy. Okay. Potential energy. Second, potential energy. The potential energy is given by 1 upon 2 sy square, where s is the stiffness for y equal to 0. For y equal to 0. Y equal to 0. That means p equal to 0. P equal to 0. If y equal to 0, then p equal to 0, and if y equal to plus minus a, the PE is maximum. PE is maximum. This is PE. Potential energy is maximum. Is maximum 1 upon 2 S. P is maximum 1 upon 2 SA square. Thus the potential energy goes on increasing. The potential energy goes on increasing. Goes on increasing. The potential energy goes on increasing. The potential energy goes on increasing as the oscillator moves away from the mean position. Away from the mean position and becomes maximum at the extreme position. Becomes maximum at the maximum its mean position and becomes maximum at the extreme position. Minimum is the mean position and maximum is the extreme position. Y equal to plus minus a as shown in this curve. You can show marked by PE. Okay. Total energy. Okay. The total energy is given by 1 upon 2 SA square, which is a constant. This is represented by the straight line. Total energy parallel to the displacement axis. Thus the total energy of the particle at any point executing simple harmonic motion remains constant, remains conserved. Okay. Thank you.